Solution equilibrium. So dissolving a solute in a solvent is an equilibrium process. We've talked about this in terms of evaporation. It's a similar idea. So you have two opposing processes. You've got the solute dissolving, and you also have the solute recrystallizing to form the solid again. So initially, you only have solute as the solid thing there, and it's going to dissolve. There's nothing to recrystallize, so the rate of dissolution is much higher than the rate of recrystallization. But as the concentration of dissolved solute increases, then the rate of recrystallization increases. So it is a dynamic process. So like sodium chloride, when that dissolves into sodium ions and chloride ions, it goes in both ways. So we have dissolving to the right and recrystallizing to the left. To the left. Here we have pictures. So there's our lump of sodium chloride. There's no sodium or chloride ions out here, and so you can't have any recrystallization occur. You're only going to have dissolving. So as these dissolve, they are surrounded by the water molecules, and so we've got these ion dipole forces going on, so we've got dissolution. Now, though, we have some sodium and chloride ions in solution, and so those can recrystallize. I think of them kind of moving in slow motion, like big balloons or something. They're just kind of floating around. And if they come over here and connect with this crystal that's still sitting there, they can recrystallize. They can say, well, yeah, that was a fun ride, water molecules, but I'm going to go back to my sodium friends over here. As these processes go on, the concentration of dissolved solutes increases, the rate of recrystallization increases until you get an equilibrium where you have dissolving and recrystallizing occurring at the same rates. Practical effects of this are if you have a solution where you have solid crystals and a saturated solution, and you leave that for an extended period of time, you come back, the crystals may look different because this process has been going on, dissolving and recrystallizing. And when they recrystallize, they tend to recrystallize in a purer form. They tend to make some really cool crystals. So a saturated solution is one where we've got that dynamic equilibrium going on. You've got the solid solute present, and you've got the dissolved solute present, and you've maxed out the solubility. So if you add more solid solute, it will not dissolve. It'll just sit there because you've already maxed out the amount that can be dissolved. An unsaturated solution contains less than the equilibrium amount of solute. So if you put more in, it will dissolve. You could try this at home with sugar or salt. Start out with a small amount of water, though, unless you want to waste a lot of sugar. Small amount of water, add some salt or sugar, stir it up. It'll dissolve. Nothing left. Add more, stir it up. You'll get to a point where no matter how long you mix it, there will be some solid left at the bottom. That's a saturated solution. You can't get more into the liquid. If you add more, you just get more solid sitting on the bottom. You can also, though, get a supersaturated solution that has more than the equilibrium amount of solute. Now, didn't I just say that was impossible? It's possible under very specific circumstances. These supersaturated solutions are unstable. The excess solute will normally precipitate. One way that you can make these solutions is by taking a saturated solution and heating it up so that you can get all the solute to dissolve, because solubility is temperature dependent. And then if you let it cool slowly and undisturbed, it may stay in solution. Then when it is disturbed, it will recrystallize. Do you remember the super cooled sodium thiosulfate we had? We cooled it down below its freezing point, but it was still liquid. And then you dropped a crystal in, and it froze quickly, right? It's the same idea here. So I've got a couple of YouTube videos to show you. So this one doesn't have any sound. Well, not really. That's saturated sodium acetate, and they just stuck a spatula in there. And that's the sodium acetate crystals. Isn't that neat? So all of the excess sodium acetate precipitates, it grows on those long crystals. And here's another one, fun with sodium acetate. Again, this is supersaturated sodium acetate. So dipping toothpicks in there. You can see that it gets hot, 52 degrees. It's sometimes called hot ice because as it freezes, it gets hot. It kind of blows your mind. So it's mostly solid there. You also make, they're not sandcastles, but as that pours out and hits the dish or the other sodium acetate, it precipitates, recrystallizes. It's a little bit like a cartoon character, like Wile E. Coyote. And here, if you let it touch the spout, the crystals will creep all the way up into the beaker. So Wile E. Coyote has run off the cliff, and he doesn't actually fall until he realizes that there's nothing underneath him, right? That's what a supersaturated solution is like. And then you say, hey, you shouldn't be able to dissolve this much, and then it'll recrystallize. So there they've spelled the word ice. You should do that. So this is sodium acetate, but it's wet. And when this is heated, it should completely dissolve. And then if we let it cool slowly, we should be able to have a supersaturated solution. So I'll try to keep an eye on that. I loosened the stopper so it won't pop out. So solubility is temperature dependent. That's why you can do that hot ice experiment. At a low temperature, the solubility of the sodium acetate is lower than it is at a high temperature. So you can heat it up and get it all to dissolve, but then when it cools down, it precipitates out. So for most solids in water, as you increase the temperature, you increase the solubility most. Sodium sulfate is an exception. So here we have solubility in grams of solute per 100 grams of water versus temperature in degrees Celsius. Sodium chloride right here has a small temperature dependence. The slope of this line is not very great. Lead nitrate has a large temperature dependence. That one's also linear. This one's linear. But some of them are curved, like potassium nitrate, potassium dichromate, potassium chlorate. And sodium sulfate is weird because when you heat it up, it becomes less soluble. Somebody always has to buck the trend. So recrystallization is a technique we can use to get better crystals, to get a more pure solid. So you prepare a saturated solution at an elevated temperature and you allow it to cool slowly. Not all substances will easily form supersaturated solutions. Most of them, when the temperature comes down, they will begin crystallizing like they should. They don't need anybody to say, hey dummy, you ran off the cliff, you should fall now. As the solid forms slowly, the crystals, they have a particular way of forming. We talked about all those different cubic structures, etc. So as the ions come in slowly, they tend to be very well organized in crystal structure, and that will exclude impurities. Some other ion comes in, it's not going to fit in there very well, and so it will tend to get excluded. And so by dissolving your solid and then recrystallizing it, you can purify it. So this is a picture of rock candy, and that's made by recrystallizing table sugar. So you look at your table sugar and it's these little crystals, but what if you want a big crystal? Well, you can make a supersaturated solution and cool it slowly and get these big sugar crystals to form. Now, if you want to try that at home, I recommend going on YouTube or somewhere and actually finding instructions for it. Because if you don't get the amounts right, it's not going to work. I tried it as a kid and it didn't work. I'm sure I just didn't have it saturated enough. But that's a fun thing. What about gases in water? Solutions of gases are very common. Tap water, water in the river, has gases dissolved in it. The gases from air. That's how fish survive. They need oxygen to breathe. They don't breathe it from the air, they breathe it from the water. Temperature affects gases differently than it affects solids. When you increase the temperature, the solubility of the gases decreases. And we can observe this in soda, which is a solution of carbon dioxide in water with other stuff as well. Warm soda goes flat faster than cold soda. That's another thing you could try at home. Pour 2 glasses of soda, put one in the refrigerator, leave one out on the counter. Come back a couple hours later and taste them. The one in the fridge is going to be fizzier than the one on the table. What this means is that oxygen levels are lower in warm lakes and rivers. So tropical fish are adjusted to living in warm water, and so they are accustomed to the lower oxygen level. But cold water fish, if you put them in with the tropical fish in the tank that's warm, are going to be gasping for air and probably will die. This is also how you can have thermal pollution in a river. So you have a factory and it's generating warm wastewater. The wastewater has been purified, it's perfectly fine to go in the river, but it's warm. As that warm water goes into the river, it warms up the river and causes the oxygen levels to be lower and can cause the fish to die. Pressure also has an effect on the solubility of gases. It doesn't really affect the solubility of solids. The solubility of a gas will increase with the pressure of the gas above the liquid. So here we have a soda can. When you flip that lid and open it, you hear that psst sound. So there's CO2 under pressure in that little airspace above the soda. When you open the lid, you release that pressure, the bubbles, the carbon dioxide begins to come out of solution. I think of it as this pressurized CO2 is like pushing CO2 into the water. It's like jamming it in there. You release the pressure and the CO2 can come back out. Looking at that a little more scientifically, here we have equilibrium. CO2 is going to have a vapor pressure. Some of it's dissolved in the water, but some of it will be up here. And we have an equilibrium. We have these CO2 molecules colliding and getting trapped in the water, and then we also have them escaping from the water into the gas state. So we have an equilibrium. We'll have a vapor pressure here. Well, it's not technically a vapor pressure because that's not, never mind. If we push down on this piston, we reduce the volume here. When you reduce the volume of a gas, it increases the pressure. Essentially, it's concentrating this, it's squeezing them closer together, and now they are going to dissolve faster because there's more of them. The rate of non-dissolving will stay the same. Eventually, equilibrium will be restored. But if you increase the pressure of the gas, you increase the solubility. It has to be the pressure of that gas, though. It can't just be any old pressure. They used to advertise these things on TV where you could pressurize your 2-liter bottle of soda, just a little pump to pump air in there. It was supposed to keep your soda from going flat. It doesn't work really well because the main components of air are nitrogen and oxygen, and the component of CO2 is very small. So you don't really get much increased pressure of CO2. So it doesn't really help with the fizzing. We can quantify the effective pressure. So that's Henry's law. The solubility of a gas in that liquid is equal to a constant times the partial pressure of that gas. Not just any old gas. It has to be the gas that we're talking about. So S is solubility. It's usually measured in moles per liter. KH is the Henry's law constant. And that's going to vary with the gas, the solvent, and the temperature. And you definitely don't want to memorize these things. If you need them, I'll give them to you. So this is a little table of Henry's law constants for different gases in water at 25 degrees Celsius. If you were using alcohol or any other solvent, you'd have to look up new constants. If you're doing it at any other temperature, you would need different constants. These are specific to water at 25 degrees. And P gas is the partial pressure of the gas. It's usually in atmospheres. The units on Henry's law constant will tell you what that should be. Capital M here is molarity, so the gas solubility in moles per liter. And ATM is the unit you should use with pressure. So determine the solubility of oxygen in water at 25 degrees Celsius, exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So we have 1 atmosphere of air, pressure, but only 0.21 atmospheres of oxygen because oxygen is 21% of air. The rest of it is nitrogen and other things. So we need the Henry's law constant for oxygen and water at 25 degrees. So let's go back here. So here, for O2 is 1.3 times 10 to the minus 3 molarity per atmosphere. 1.3 times 10 to the minus 3. (1.3 times 10 to the minus 3). Didn't look very good. Molarity per atmosphere. And Henry's law tells us that the solubility of the gas, here it's O2, equals the Henry's law constant times the partial pressure of the O2. This is the partial pressure of O2. So the solubility will be 1.3 times 10 to the minus third molarity per atmosphere times 0.21 atmospheres. So this will be pretty small. .73. In terms of significant figures, the partial pressure and Henry's law constant only have 2. So we're going to keep the 2 and the 7 and get rid of the 3 times 10 to the minus 4 moles per liter. Any questions? If you take a cup of water and you heat it, it helps to do it in a clear container. You heat it, you can see little tiny bubbles forming as it heats up. It's not boiling yet. What you're seeing is dissolved air coming out of the water, because as the temperature increases, the solubility of the air decreases.